So number 35,
Mm-hmm.
lung cancer hazard rate. Okay. So chapter 5, number 35. Wait, am I looking at the right one? Is that the right one?
Yes. Yeah.
Okay, lung cancer hazard rate, lambda of T of a T-year-old male smoker is such that lambda of T is equal to that function. Assuming that a 40-year-old male smoker survives all other hazards, what is the probability that he survives to age 50 or age 60 without contracting lung cancer? Okay, so this is kind of like two parts, but if we could get one of those, I think the other one should be fairly doable. So what is the definition of the hazard function? What do you do? Isn't that where you like take 1 minus the, hold on a second, that was back, where's that defined?
Page 201.
201?
Mm-hmm.
Right. So, yeah, that's right. You take the complement of the CDF, right? And that ends up being the denominator. And then you take the actual density and divide by the complement of the CDF. Okay, so what you end up getting is basically, well, I mean, you have the density function, and then on the bottom, that down on the bottom is actually the probability that the random variable in question exceeds that value T, correct? And they kind of give an interpretation for that, which is somewhat helpful. It says, to interpret lambda of T, suppose that the item has survived for a time T, and we consider that the probability it will not survive for an additional time dt. Okay, that is, consider the probability that x is in t plus t, or t comma t plus dt, so that it's in the interval from t to t plus dt, okay, where x, I guess, is supposed to be the lifetime of something. Is that how they define this? Right. X is supposed to be like the lifetime of something. By the way, lifetime of an object, a lot of times that's modeled with the exponential distribution, for instance. Okay. But the probability that X has survived T, but will not survive an additional time dt is given by that probability. It's a probability that X belongs to the open interval from T to T plus dt, okay? Given that X is already above T, so it's already lasted T years or T minutes or whatever it is. Now, why is that probability? Okay, so why is that an open interval on the right-hand side of that? So X belonging to T comma T plus dt. Why is that an open interval?
Is that because it's continuous?
Well, but they said it will not. It says, suppose that it already has survived for a time t, yeah, but it will not survive for dt more time, okay? So that means that X, which kind of describes the lifetime of this thing, it's already beyond T, but it is not going to be beyond T plus dt, yes?
Okay. Mm-hmm.
So that's why it's an open interval on the right-hand side, because it's saying this thing is going to die before dt more units of time, yes? Does that kind of make sense?
Mm-hmm.
Okay, so let's kind of continue to read the interpretation. Now, the probability that x belongs to this open interval t plus dt, given that x is bigger than t, okay, what's that equal to? Well, it's equal to the intersection of the probability of the intersection of those two events. That's what's upstairs. Probability that x is in t and t plus dt, and x is bigger than t. But look, that over the probability that x is bigger than t, right? That's just the formula for conditional probability. When they put a comma, that's the same thing as like an intersection, okay? But seriously, everyone, if x is in the interval from t to t plus dt, and x is bigger than t, we only need one of those two things. Which is the thing that kind of subsumes the other one?
So the interval.
The interval itself subsumes the other one, yes? If x is in the open interval from t to t plus dt, then x is automatically bigger than t, yeah? I mean, it's just automatically there. So they just drop that second event, okay? And just deal with the interval itself. And then they divide by the probability that x is bigger than t. But the probability that x is in t comma t plus dt, that's going to be gotten at through integration, isn't it? I mean, the probability that x belongs to any interval is gotten at through integrating the density, yeah? And what they're saying is dt is like an infinitesimally small amount, right? So, I mean, basically that's just going to be like f of t, you know, whatever the value of the density is at t times this tiny dt thing, yes? So that's why they have that. And then on the bottom, the probability that x is bigger than t, that's the complement of the CDF. Does that make sense? So it says, thus, lambda of t just represents the conditional probability intensity that intensity is like the word they use for, well, it's weighted by dt, like this infinitesimal, yes? It's the probability intensity that a t unit old item will fail, okay? And so that's where that formula f of t divided by the complement, or the density at t divided by the complement of the CDF comes from. Hopefully that kind of makes sense where that came from. I mean, they just computed this probability and they said, look, I mean, it looks to me like the lambda of t function, which is sitting right there, is essentially kind of like the density of you know, when this thing is going to die, okay? So they do a couple of examples there. They do an example. I think I pointed this out the other day. I think you asked about this. I pointed out that they computed it for the exponential distribution, and that ends up just being a constant, correct? Really, the exponential distribution is the example that motivates this thing in the first place. You just have a constant hazard function in that case, namely lambda, the parameter of the exponential. Okay, so I just wanted to give you a problem that kind of deals with one of these. The lung cancer hazard rate, lambda of t, of a t-year-old male smoker is that. Now I'm just reading this problem again. Assuming that a 40-year-old male smoker survives all other hazards, what is the probability that he survives to age 50, say? Okay. So what do you guys think? What does lambda of t equal to? I mean, they gave us a formula, right? But what is lambda of t equal to in general? Anyone?
Just the PDF over the complement of the CDF.
Right, it's the density divided by the complement of the CDF, yeah. So why is that helpful? I mean, they asked me for a probability, correct?
Mhm.
Sorry, I need to actually get into Zoom here. Oh man. Okay, here, let me get myself in here. Okay. Oops, what did I just do? Seriously. Okay. Go like this. Okay. So what do you guys think? We have lambda of t equals 0.027 plus, what is it, 0.000 times t minus times t minus 40 squared, and this is for t equal to or greater than 40. Yeah. And on the other hand, you know that this thing is equal to the this thing is equal to the density divided by 1 minus or here, let me write it this way. Divided by the probability that, okay, so what is the probability to survive? So let's say that x, let's kind of define a random variable. So x, let's just say that x is equal to survival time. Okay. Okay, so this on the bottom, it's going to be the probability that x is bigger than t. That makes sense? And what do we want to do? We want to compute the probability that what?
That
That
x is
x,
greater than 50.
okay. 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 Is that it? So how do we do that? How do we do it? Any ideas? What did you guys try?
Initially, I tried integrating it and then plugging in like from 0 to 50, but I wasn't really sure if that's the right way to go about it.
Okay. Right. So first of all, what you do know is that what do you know? Okay, so let's kind of think about this. We know that if you plug in 50 into this, right? So you know that f of 50 divided by the probability that x is greater than 50 is equal to lambda of 50, okay, which is, what is this going to be? 0.27, right? 0.027 plus, what is that going to be? If I plug in t equal to 50, I'm going to have 100 times this thing. So is that going to be 0.025? That makes sense?
Mhm.
Okay. So what does that mean? 0.052 or something? Okay. Okay. So one thing that you do know is that the probability that x is greater than 50, at the very least, this is equal to f of, right, it's equal to the density evaluated at 50 divided by, it's equal to the density evaluated at 50 divided by 0.052. Okay. So that's at least something. But the issue is we don't really know what the density is, correct? So is there anything we can do to get our hands on the density at all? What do you guys think? Because we want to know this thing, right? If we could sort out what the value of the density is at 50, we'd be in good shape, wouldn't we? Do you agree? Yeah. So how do we do that?
Would we use the exponential distribution?
Did they tell us it was the exponential distribution though?
No, I guess not.
I don't think it could possibly be the exponential distribution. Why not?
Well, I guess it's not necessarily behaving in the same way that would. I just kind of viewed it as the amount of time before the first occurrence being like not surviving.
Yeah, because the exponential distribution, what do we know the hazard rate? Like there was that example back there, right? What did we learn about the hazard rate for the exponential function?
But that's just a constant.
Yeah, that's always a constant. And this thing isn't a constant, right?
Mm-hmm.
So,
So we're trying to find the density of this? Is that the goal right now?
well, we don't actually need to know the density exactly, but I mean, because we just need to know what the density is at 50, right? If we could just figure out what the density actually was at 50, we would be done. That makes sense?
Could we use any of the equations that are on page 202? Right, I accidentally skipped this problem because I didn't mark it in my book, so I'm just looking at it, but they have like later down further in the page, they have like capital F of t is equal to 1 minus e to this integral. Could we use that possibly, or is that not?
Yeah, so right. So look at what they do here, okay? So what they basically have is this. That's good. So if you have, okay, so, you know, they have to use a different variable because they want t to be in the integration constant. So if you integrate the hazard function from 0 to t ds, then what is this? This is the integral from 0 to t of what? Little f of s over 1 minus capital F of S ds, right? And one thing that we notice is that, hey, remember that the density is like the derivative of the CDF. Do you remember that?
Mhm.
Right. So F of S is the derivative of capital F of S. Right. Little f of S is the derivative of capital F of S. So what they do is they say, look, this is like minus, and of course, you know, being a more advanced text, they use log for like the natural logarithm. Okay. For mathematicians, eventually there's no other logarithm other than the natural logarithm, okay? I mean, why would you talk about anything else? They write log, but in common parlance, that means the common logarithm base 10. But what we really have here is minus the natural logarithm of 1 minus capital F of S, right? That's the antiderivative of this, because think about it, when you take the derivative, it would be minus 1 over 1 minus capital F of S times the derivative of the bottom. The derivative of the bottom is going to be minus F prime, capital F prime of S. But that's just minus little f of S. And the minuses cancel, correct? So then they evaluate this between like 0 and t. Okay, and what are we left with here? Minus natural logarithm of 1 minus f of t minus negative, which is plus the logarithm of 1 minus capital F of 1. And so what do we end up with here? Isn't this just going to be logarithm of what? 1 minus, right? Because it's one logarithm minus another logarithm is the logarithm of the quotient. This is 1 minus f of 1 over 1 minus capital F of t. So look at that. If you integrate the hazard function from 0 to t, we get this nice little equation right here. Oh, sorry, it's not f of 1. What should I have here? F of
0.
Yeah, f of 0. That's right. Yeah, and this is f of 0. And did they say something about f of 0? Basically, what they're saying is, you know, okay, 1 minus, okay, what's f of 0? So what is f of 0? What are we going to assume about f of 0? What do you think we're going to assume about capital F of 0? Right, x is a survival time, correct? What do you think the probability that x is less than 0 is?
0?
Yeah, that should be 0. Does that make sense? So, so what we end up with here is this is like the logarithm of 1. There's 1 minus 0 here, so it's just the logarithm of 1 minus capital F of t raised to the -1 power. Yeah? And maybe, just maybe, that would be helpful to us. Okay? In fact, it seems to me that we could actually solve this thing for capital F of t. Doesn't it seem like we could somehow? How? How could we solve this for capital F of t? What would I do to both sides of this equation? Right, this is equal to this. Can't I solve for f of t somehow? What would I do?
Do you want to multiply through by e?
Well, you raise e to the powers on both sides, yes. Okay, so then we get that 1 minus f of t to the negative 1 is equal to e raised to this integral, whatever it is. Okay. Okay. Which means like okay, this thing raised to the minus 1 is like 1 over that thing. So this is the same thing as saying that 1 minus f of t is equal to, I would just have to invert both sides. So this would be e to the minus this integral, the integral from 0 to t lambda of s ds. And so do you see that f of t, capital F of t, is equal to 1 minus this exponential, e to the minus integral from 0 to t lambda of s ds. Amazing. We actually come up with this thing. So it seems like we could potentially even just get away with not knowing. This is sort of amazing. Looks like we don't even really have to necessarily know this thing right here. Okay. So yeah. What did we, well, actually, I mean, both of this version up here and this version down here are both useful. What did we want to know in this problem? We actually wanted to know the probability that x was bigger than 50, right? So what we really wanted to know, we wanted to know the probability that x was bigger than 50. So we really wanted to know 1 minus, the probability that x is bigger than 50 is 1 minus capital F of 50. You understand? Yeah, isn't that true? We want to know 1 minus capital F of 50, which is going to be, according to this thing, e to the minus integral from 0 to 50 lambda of s ds. Yeah? This is the probability that x is bigger than 50. Isn't it? So I just need to do e to the minus whatever that integral is from 0 to 50. So let's go ahead and do that. What was the integral that I was supposed to do? What was the integrand? It was lambda of t. Or actually here, let's not use t right now. Let's use s, okay? It was lambda of s equal to something. What was it? So can you read it off to me? It was
0.027 plus
0.00025, and it was t, or oops. Was it s minus 40 or something?
Yeah, squared.
Okay, and this was for s equal to or greater than 40, right? So if I want to do the integral from 0, let's do a generic from 0 to t, just so that we can use it twice if necessary, yeah? And not reinvent the wheel. The integral from 0 to t lambda of s ds, what's that going to be? What is the antiderivative? Okay, so, okay. What's the antiderivative of 0.027?
0.027 s.
Yeah. And what is the antiderivative of this other thing? What's the antiderivative of that other thing?
Point 0.00025 times a third, or over a third, s minus 40 to the third.
Okay, and this thing's being evaluated between 0 and t, right? If I plug in t, I get 0.027 t plus 0.00025 over 3, t minus 40 cubed, okay? And then I have to subtract this thing off evaluated at 0, correct? And what's that going to be? Basically, the only thing that's going to survive when I plug in 0 is the part that has the cubic in it, correct? So isn't that going to be 0.00025 over 3? And isn't this going to be 40 cubed? Is that right?
Negative 40 cubed.
Put this into a plus, right?
Okay.
Yeah, so let's just turn that into a plus. Good. Okay. So then what do we want? So the probability that x is bigger than t, which is 1 minus capital F of t, this is going to be e to the negative, the integral from 0 to t, lambda of s ds. Okay. And we actually have that thing right here, don't we? Don't we have that thing right here? Right, I mean, there's going to be a minus sign right here, but I can just straight up plug that thing in. So what does that end up being? You guys maybe plug in for 50, the probability that x is bigger than 50 is equal to e to the minus the integral from 0 to 50 lambda of s ds, which means we need to plug in 50 into that thing. What do we get? Minus, okay, if I plug 50 in, what do I get? .027 times 50 plus 0.00025 divided by 3 times, what is it? I'm plugging in 50, so it's going to be times 1,000. Is that right? Because it's 10 cubed. And then it's plus 0.00025 divided by 3 times, what do I have, 40 cubed? The third power. Okay, I get like 6.76 repeating or something like that. Is that what you guys got? And then I'm going to take e raised to that thing. Let's see. E raised to that. Oops. No. To the negative of that. What? Okay, so clear. So e to the, what in the world is going on here? So e, my calculator's not doing well right now. Where is e? I think the problem is my my daughter actually messed with my calculator. Negative 6.766666 repeating, yes. Yeah, it's not letting me do it. She's got this thing in some kind of mode that doesn't work. Can someone put that into their calculator though? 1 over e raised to that power. What do you get? I mean, I could do it in Wolfram Alpha here.
Well, I just got 0.0011516, etc. But that's kind of small.
Uh-huh. That makes sense. 00115 what?
16.
Okay. Yeah.
So, are you supposed to integrate from 0 to t?
What do you mean? What? So for what?
The hazard rate function's only defined for t greater than or equal to 40.
Oh.
So when I did the problem, I just integrated from 40 to t.
Oh, yeah, I think that's probably right, Matthew. Right, so that would change this, wouldn't it? That would change this to what? To 40? Okay. And doesn't that make it easier on, it makes one thing easier, I guess. Well, I guess not really. Well, this thing right here would change to what? Instead of a 0.0025 40 cubed, what would you get?
0.
Yeah, this thing would be 0. But then the other thing, what would the other thing be? Would it be like a minus 40 times that or something? Is that right? So you get like 1.08.
Yeah.
Okay, so this is the function that we should have been using right here. Sorry about that. So then you would plug in things that are above 40 to get this. Okay, so what is that? If you plug that in, if you plug in t equal to 50, what do you get? 0.027, oops, 0.027 times 50 plus 0.00025 divided by 3 times 1,000 minus 1.08. You get 0.35 something. Okay, so this thing right here should have been 40 to 50. Yeah. And this thing right here should not be this. It should be 0.35. 3 repeating. And what does that change it to? What does that change it to?
I'm getting 0.702.
Okay.
I don't know if that's right though.
Okay. So that would be the new probability if we only went from 40. Right? Is that the right answer?
This didn't have an answer. I don't
Oh,
think.
okay. Well, I'm pretty confident that is that what you did? You did that? That's what you did, Matthew?
Yes.
Okay. You got 0.702?
Yeah.
And you guys understand what you would do for the case of 60. You would simply change the upper limit of integration to 60 instead. Okay. That's just a little computational exercise. Get the old probability juices flowing a little bit. Does that make sense? It's a little lesson in hazard function stuff. Again, that's not what I would consider to be like a critical issue. That's something that you could kind of learn in a day if you had to, if you were in the actuarial discipline or something. And hazard rate functions do come up, in that venue, no doubt, right? But it's something that you have the tools to kind of learn. So, what else? Other questions? You have other questions?
Can we talk about problem 39?
Yeah.
Which you kind of answered part of my question earlier because I wasn't quite sure what that log was referring to and if it was a natural logarithm or not.
Yeah.
But this one also does not have an answer in the back, so I don't really know if I was doing what I was supposed to on this one.
Okay, so what do you have? You have that x is exponential with parameter 1. Is that what they tell you?
Yeah.
Okay. And now what? So you know all kinds of stuff about x, like you know what its density is, what the CDF is for this thing. I mean, the exponential is like super nice, right? So what about a y, which is the logarithm of this thing? Okay, so y is equal to the natural logarithm of x. Okay. Well, why don't we just go ahead and try to like compute? Let's compute the CDF of this thing. Let's see what happens. Why not? Why not, right? Okay. So I'm doing capital F sub y of little y. That's the probability that y is like less than little y, correct? But what is y equal to? Well, it's the logarithm of x, correct? Okay. And so that would mean the logarithm of x is less than y. Okay. And that's the same thing as the probability that, hey, you know that exponentiating, since the exponential is an increasing function, it's going to preserve the direction of this inequality. Yes? If I exponentiate both sides, what do I get? X less than?
E to the y.
E to the y. Okay? Crying out loud. We know a CDF for this thing, correct? That's just going to be capital F sub x of, I mean, look, all I'm doing is plugging in the number e to the y into this thing, correct? What is the CDF for, what is the CDF for the random variable x? What is that? Isn't it 1 minus e to the, isn't it 1 minus e to the minus lambda x, correct? Yeah? But what's lambda equal to here?
1.
Yeah, so it's just 1 minus e to the minus x. And what are we taking x equal to here?
E to the y.
E to the y. So look at this crazy nonsense. The CDF of the random variable y ends up being 1 minus e to the minus e to the y. That's amazing, right? But they wanted the density. Well, what do I do now? I just found the CDF. I just found the CDF of y. It's given by that, correct? How am I going to find the density? By the way, I'm pretty sure that y could be anything at all. Because isn't, like, y is equal to the logarithm of y is equal to the logarithm of x. And doesn't the logarithm of x, where x is anything that's, you know, bigger than 0, the logarithm of x is going to produce any number at all, right? The logarithm, it runs through all possible numbers, correct? So, I mean, in theory, I would have to take any number that's between minus infinity and infinity. So this CDF is for y belonging to minus infinity to infinity. Okay? So how would I find the density? What would I do?
Wouldn't you take the derivative of it?
Yeah. Yes. What's the derivative? Well, it's going to be, right, because it's e to something, so it's going to be itself times the derivative of the power, correct? The 1 goes away, but it's going to be itself times the derivative of the power. The derivative of the power is just minus e to the y, correct? So the minus signs are just going to go away, and you're going to end up with e to the y, e to the minus e to the y times what?
E to the y.
Yeah, e to the y, which if you really want to be extra clever, you could write this as e to the, since both have the power, since both have the base e here, I could put everything up in the power. This is just e to the y minus e to the y. You see what I'm saying?
Mm-hmm.
And there's the density. And what's so weird is apparently this should integrate to 1. You know what I'm saying? Okay. Let's check that. That would be really something amazing. Okay, so let me go over there and we'll do that. Maybe that'll be a good place to stop for now. Okay, here's Wolfram Alpha. Can you guys see this?
Mm-hmm.
Okay, watch this. I always like, okay, so integrate. What is it that I wanted to integrate? It was e raised to the y minus e to the y from negative infinity to infinity. We'll see if it understands this. Hey, check that out. You get 1. That has to be right. Okay. Wow, that's amazing. Oh, I think I know why. Maybe I'll do this real quick and then we'll call it a day. Oops, what am I doing here? Oh, I know what to do. Watch. Okay, here we go. Okay, here we go. Go over here. So watch this. I mean, this is just good practice for you guys. So if I were to integrate from minus infinity to infinity, I don't know, I'm sort of regretting putting those things together. E to the y times e to the minus e to the y dy. What could I put u equal to? Help me out. What could I put u equal to for sure? What do you guys think? How about e to the y? Yeah? Then what's du?
E to the y.
E to the y dy, which is exactly what we see right here. Know what I'm saying? This is the same thing as the integral of e to the minus u du. And by the way, what's my new limits of integration? If y goes to minus infinity, what does e go to? Or sorry, if y goes to minus infinity, what does e to the y go to?
Zero.
0. And if y goes to infinity, where does u go?
Infinity.
Yeah. And what's the antiderivative of e to the minus u? How about minus e to the minus u, correct?
Mm-hmm.
And this thing is evaluated between 0 and infinity. E to the minus infinity, that's like 0. Yeah? I'm letting you go to infinity. I go minus negative, which is plus e to the 0, which is 1. Yeah, which is exactly what we had hoped and dreamed about. Yes. Wolfram Alpha verified it, and we just verified it by hand. So there it is. Yeah. All right. So let me stop sharing this. Okay. Hopefully that was somewhat helpful. Did that kind of get some of your questions answered there?
Mm-hmm.
Okay. Yeah. Anything else? So Emma, is your internet situation better now?
Well, we're considering me needing to go to my friend's house for internet a necessary item, so I'm not obeying the stay-at-home order.
Oh, okay. Okay. How far away is that?
It's about a 35-minute drive for me.
Okay, so are you just kind of going and hanging out there during the day and then going
Yeah.
then?
Mm-hmm.
Okay, so is that working out all right for you then?
So far.
Okay. And where did you say you are?
I'm at my friend's house,
What state?
Michigan.
Oh, okay. Okay. All right. Yeah. You guys hanging in for the most part?
Yeah.
Okay. So check this afternoon. I'm going to post, a little problem for you to work through for Friday. I'll just, sort of pick one at random from the homework set. Not really. I'll sort of pick one that I think is most prudent for you to work through or whatever. But you'll have about a 48-hour turnaround on that. Hopefully that'll be more than reasonable given what I'll ask you to do. Okay. And by the way, chapter 6, I'm just kind of warning you, it's an excellent chapter to read through. There's lots and lots of information that you really can kind of drive yourself crazy with. There's just tons of information. The same thing kind of happens in chapter 5, but I'm just picking bits and pieces that I think are most important. So what I'm going to spend some time on, like on Friday, for instance, is I'm going to spend some time on distributions of sums of random variables, because that comes up a lot in probabilistic practice. Okay, it's like if I have two instances of a random variable and I add them together, what's the distribution of that thing? So if I have two things that are binomial and I add them together, what do I get? If I have two things that are Poisson distributed and I add them together, what do I get? Okay, those are legitimate questions that we should be able to answer given the tools that we have. So I'm going to spend some time on that. That will be very different from the stuff that the prob and stats people will be doing. They're going to be moving more into statistics applications at this point. But we're going to kind of camp on some of these more nuanced questions related to random variables, distributions, and what happens when I start taking sums of things. I already mentioned that I'm kind of been gallivanting around in chapter 7 a little bit. There's some stuff in there about correlation and whatnot, which I hadn't planned on talking about till I was in chapter 7, but I went ahead and brought it back into the context back here just so that you have it in your cognition already. Okay, so that's kind of where we're headed. Believe it or not, I mean, I kind of stopped paying attention to the schedule when all of this started happening. But believe it or not, I'm not that far behind. I was sort of surprised. I went and checked that out and I was like, oh, wow, we're actually doing decently well. So I don't know that we'll get through everything I wanted to get through, but I think for sure we'll get through at least chapter 7. And there's some good stuff in there for us to finish up our probability theory explorations with. Okay. So that's just kind of a vision casting for where we're heading in the next week or so. Man, we still have like a month left, right?
Yeah.
Is that true?
Mm-hmm.
Finals week ends a month from today. Yeah.
Oh man. Okay, so that's crazy. Okay, so I guess we only have, I guess it's only like 3 weeks of actual class left or something, right? But yeah, I think Easter's in there somewhere. But yeah. All right. Hey, thanks for coming in and asking good questions. Appreciate that. It's always helpful. All right.
Thank you.
All right.
Thank
See
you.
you later.
Yeah, thank you, Dr. Hammett.
Yeah.